this is where we were. So we proved that given some measurable mu from omega into C, absolute value of mu is less than equal to lambda, which is strictly less than 1 almost everywhere. Consider mu to be 0 outside of omega. Then there exists P bigger than 2, close to 2. Such that defining this function f to be the Cauchy-type transform of 1 minus mu of the Beurling transform to the minus 1. This thing acting on mu itself solves the following Beltrami type equation. Almost everywhere in the complex plane, like this. Because as a corollary of defining it this way, we have that f itself has weak derivatives that are LP functions. In other words, it's a Sobolev function. Okay? So, because we know that df by dz is, when we act on with the conformal part of the gradient on the Cauchy-type transform, we end up with this guy of mu, and we showed that this thing makes sense as an LP function, in this case for any p which is bigger than 2. Okay? And if we take p sufficiently close to 2, then this thing is a well-defined thing, and therefore S acting on it is also going to be an LP, because that's our standing assumption that the Beurling transform maps LP to LP. You know? So this thing does have a gradient, and it's equal to this LP function. It's a Sobolev function. Well, it's a Sobolev function because we also know, sorry, this belongs to LP. It's a Sobolev function because also the anticonformal of the gradient exists, because when we take the anticonformal part of this Cauchy transform, we just end up with this function itself, right? Which again is an LP. So, right? So these guys are the entire gradient of f. So the gradient of f is an LP function. So we are saying that this gradient as an LP function is equal to mu times this LP function plus mu almost everywhere. Okay, that's where we were. Cool. And then we defined g of z to be equal to f of z plus z, like this, and then it was just some algebra from this equation that g by dz bar is equal to mu, z on the complex plane. Yeah? Cool, because we just factor out this mu, and then we notice that if we take the anticonformal part of the gradient, we just end up with the anticonformal part of f, because this vanishes, but the conformal part of the gradient will be conformal part of f plus 1, and then that's exactly how this falls out. Yeah? Cool. So, well, I mean, we need to have these relationships right here. We need to have this way to build algebraically this stuff right here. And the magic about P is that, I mean, P is just a constant. It's just a constant difference. It's just a constant depending on the function difference away from the Cauchy transform. And the magic of that is that the Cauchy transform has these relations that if we take the conformal part of the Cauchy transform of a function, we end up with the Beurling transform, right? And if we take the anticonformal part of that's how we started this whole stuff. This ends up with a function for smooth functions, you know? And then the fact that we could define this for functions in LP and the Cauchy transform, sorry, start again. The fact that we went to P was because for the Cauchy transform, we weren't, you know, that was how I messed things up before. We can't define this for arbitrary functions in LP because the growth at infinity is not going down fast enough. Yeah? So we make this adaptation, P of F, which is like the Cauchy transform. So let's try it like this. So P of F on some Z is like the Cauchy transform. And then it's plus just some constant depending on the function. So let's call that, say, W of F. So it doesn't depend on Z, right? Just so that these differential relations continue. We can still do it. And now we can talk about F being inside LP, you know? And then we have these nice continuity properties, so that allowed us to replace this thing, which was only true for F, which was smooth. Well, it's also true for C2, but let's just say C infinity, compact support. We can replace these relations with the weak relations, where these things hold true weakly for an arbitrary function in LP. That's the main point of P, or at least going from C to P, is that now we can formulate these relationships, you know, for arbitrary LP functions and have them be true. We can have these relations be true, and now because the right-hand side is LP, if F is an LP, then what we have now is that for the Cauchy transform, we have that the function we create. So again, for the Cauchy type transform P, we have that the function we create is actually a Sobolev function. This now is a Sobolev function whose derivatives exist. Yeah? Does that help? Does that get you to the heart of your issue? Yeah. If you were trying to do it a different way and it seems to work to you and you don't see why we have this structure, yeah, just come in and talk with me and we'll see. I'll see why it doesn't work. Or maybe it does work under some additional assumptions. Okay, so we are here. We are here with this guy. And the only additional thing we need in order to have the result we want to establish the Stoilov decomposition and get all the good stuff for quasi-regular mappings is that G is an invertible mapping. Right? We want G to be an invertible mapping. And G is just like the identity mapping plus F. Right? So what I claimed on Wednesday was that as we go out towards infinity, the gradient of F goes down to 0. So this mapping is more and more like a flat mapping. Yeah? And I gave you some sketch about why you should believe that if you have a mapping whose derivative is strictly positive almost everywhere, and it is flat towards infinity, then it's actually going to be invertible. And that actually show that for an arbitrary Sobolev mapping, that's non-trivial. That's using some degree theory for non-smooth mappings. But for smooth mappings, it's easier to see. And I tried to come up with a model for how to see this. So let me just state where we're going, and then I'll try and explain. Well, at least the metaphor. So we want to show that the gradient of F just gets closer and closer to 0 as we go off to infinity. So notice that outside of omega, mu is equal to 0, right? So the conformal part of the gradient is, sorry, the anticonformal part of the gradient is nothing outside of omega, so it's actually holomorphic. Yeah? So if it's holomorphic, there's only one gradient. That's what holomorphic means. It's differentiable, so there's only the derivative exists in just one sense. So we want to show that f prime of z goes to, so last time I mean, this is actually true, this is called the principal value, that this is actually less than a constant times mod z. This is as z goes to infinity. The argument I'm going to give is something that is a little bit weaker, that this is less than c over constant over mod z to some alpha, where for any alpha which is positive but less than 1. Okay, that's what we're going to show. And that's going to be enough for our purposes, because it means that G is looking more and more just like this identity mapping, and more just like it's flat. So here's the metaphor for why you should believe that if you have a smooth mapping whose derivative is strictly positive everywhere, and it's close to the identity outside, then it's going to be invertible. Can you see this thing here? Can you see this plastic bag with this circle with arrows I drew around? Yeah? Just about. Hey, what if I step in front of the board? Yeah, I mean, degree theory is a lovely thing to learn. It's a very pretty and useful subject, and slightly tempting to talk about it, but that's not really the topic of the course. So I'm just gonna talk in metaphors and not give you a fully rigorous proof of this part. I'll give you a kind of a sketch argument in a bit. But what we would need for that to work is for this thing to be true in order for us to say that around the outside it's more and more like an affine, just like the identity mapping. Yeah? Cool. So our next thing we're going to do is establish this, and then we'll have some sketch of how we could do this with a more formal mathematical argument, assuming things are smooth and other nice things. Cool. That's where we're going. So I suggested you thought about this with power 1 as an exercise, and then later I realized that the argument I had in mind doesn't quite give power 1. So yeah, if you did that and didn't succeed, do not worry, because I didn't succeed either. I mean, it is true, but it's more complicated arguments than I had in mind. We're going to do this, and that's going to be good enough for us, and we're just going to use properties of harmonic functions to establish this. And this is how we're going to go with this stuff. So, going back to here, what do we know? We have that the conformal part of the gradient is an LP. Yeah? And that's true for any P which is bigger than 2. That's what we have. Yeah? And what is the conformal part of the gradient? So part of gradient is this Vertinger derivative, which is 1 over 2 d by dx minus I d by dy, like this. And if we apply this to a holomorphic function, so for z not belonging to, I mean, what I'm about to say is obvious, well, not obvious, but it's clear for lots of reasons, but let's just do the algebra. If we have z not belonging to omega, then it's holomorphic. So then satisfies Cauchy-Riemann equations. So if we let f be u plus iv, then we know these equations well at this point. Yeah? So, if we apply the conformal part of the gradient to our function f, let's just see what happens when we take the partial with respect to x. Well, that's just going to be the same as the complex derivative because it's holomorphic, right? So d by dx of f, which is u of x plus I v of x, that is just equal to f prime, the complex derivative, because that's just taking the derivative direction, the real numbers. Yeah? And if we do d by dy, oops, I should have put f prime here. And if we do df by dy, then it's going to be u of y plus I v of y, like this. Yeah? But that thing, when we use Cauchy-Riemann equations, that thing, this is becoming minus v of x, and then this guy is becoming plus I v of x, u of x. So if we factor out an I from this, then we have u of x minus v of x over I, which is the same as I times u of x plus I v of x, which is I times the complex derivative again, like this. Yeah. So then, in this conformal Vertinger derivative, when we do this, we have 1 over 2 df by dx minus I df by dy, yeah, and that is equal to the complex derivative. D by df is just the complex derivative, and then this guy, df by dy, is just I times the complex derivative, but then it is minus I times I, so then it's going to be, again, f prime of the complex derivative. So this whole thing is just the complex derivative. Yeah? Which is no surprise, right? Because this is the conformal part of the gradient, and that is the only gradient we have once we are in the holomorphic part. Yeah? So that means that we can use this relationship, because what this means when we're outside of omega is just the conformal part of the gradient. Sorry, what this means when we're outside of omega is just the standard complex derivative. So we have the standard complex derivative is integrable in LP. Yeah, that's what we know. Cool. All right, I'm going to erase the board, and we're going to use that. We have that again. That df by dz belongs to LP of the complex numbers to the complex numbers, and let's also call that f is hollow on, so you take omega. Now, f is equal to u plus iv, right? F is holomorphic. And that means that the coordinate functions u and v are both harmonic, right? So Laplacian of u equals Laplacian of v, which is equal to 0 in the complex numbers take away omega. Yeah? And they're also smooth, so I can just take the derivative through. Yeah? And so we also have that if we, for example, take the partial with respect to x, and then take the Laplacian and the partial with respect to x of v, take the Laplacian, that's also equal to 0. So the first partial with respect to the x coordinate of both u and v are harmonic too. Yeah? Yeah? And what we know about this, we also know from what we just seen that this guy is just u of x plus I v of x. So that means that if we just take the first partial of x, then this thing belongs to LP, at least in the complex numbers, take away omega into the complex numbers, because outside of omega, then u of x is just the real part of this thing, and therefore the absolute value of this thing is bigger than the absolute value of just u of x, and therefore u of x is an LP. Do you see what I mean? Thumbs up if you're with me here. Yeah, so we know that the conformal part of the gradient is in LP, right? So what does that mean? That means that if we take the double integral of the complex numbers of the absolute value of the conformal part of the gradient in the LP sense, dz, then that's finite. But this thing is just a complex number whose real and imaginary parts outside of omega is just given by u of x, v of x. So df by dz, dz like this is just bigger than u of x, right? In fact, if we just, this is equal to u of x squared plus v of x squared. So this means that, this is what we said, that this guy is in LP, and it's also true for this thing, v of x, for the same reason. Thus, they are harmonic mappings, they are harmonic functions, and they satisfy the mean value property that when we integrate them over a ball, then the average of that, then we are back to the value of the function at the center of the ball, right? So we're going to assume omega is bounded. So I should maybe say that. Assume omega is bounded, and that's not necessary for the general theorem, but that's what we're just going to do. Assume omega is bounded. So there exists some r bigger than 0, such that omega is contained within a ball of radius r. Right? So let us draw a picture. So this is the ball of radius r, which, say, omega is contained within. So this is omega, this is 0, this is r. So if we take, I think I call it capital R, right? So then if we take some mod z, which is bigger than, say, 2 times r. So take z, which is in the complex plane, take away the ball of radius 2 times r, like this. Then since we know that mod z is bigger than 2r, and that means that if we take a ball of radius mod z over 2, then we will not intersect this ball of radius r, right? So the ball of mod z over 2 around z intersect the ball of radius r will be equal to the empty set, like this, right? Because this is r. We are bigger than 2r away. This is mod z. And then mod z over 2 will not intersect r. Okay? So that means we're completing the holomorphic part of the function, right? So by the mean value property for harmonic, what do we know? We know that u of x of z is equal to the integral around the ball of radius mod z over 2 times mod z. That's right. Let's do the double integral just to remember that we're doing this as solid. We're doing the integral of the solid ball. And let's write w. And this is, this is a function of x and y. So, right, just dw, but it's a double integral in the standard sense in a plane. And then divided by the area of this ball. And the area of this ball is pi times mod z squared over 4. Right? So that's true just by mean value property. Yeah? But then let us use the fact that we have that, oops, and this should have been the partial with respect to x, because this is the harmonic function we're using. And then let's use the fact that we have that this guy is an LP. So double integral of this thing, mod z, u of x, let's take the absolute value, dw, that is less than, applying Holder's inequality, it's less than the LP norm of u of x on the entire complex plane, take away omega. And then the product we're applying it to is just a function, is just the number 1, right? So then times integral of just the ball of radius mod z over 2 times 1 to the Holder conjugate p prime 1 over p prime. Yeah, just Holder's inequality. This thing is something which is just finite, that's given to us. Let's look at this guy. So again, u of x, LP norm, complex numbers, take away omega, like this. This thing, it's going to be the volume of the ball, right? Because 1 to any power is just 1. So it's the volume of the ball to this power 1 over p prime. And let's look at what 1 over p prime is. So these are conjugate pairs. So 1 over p plus 1 over p prime is equal to 1. So 1 over p prime is equal to 1 minus 1 over p. Yeah? So what is this? This is this times, so I don't want to care about the constants because the constants are all gonna vanish. So they're all just going to be fixed constants. So I'm just going to bound it by some c, and I'm not caring about this. All I'm caring about is that the volume of the ball of radius mod z over 2 is of order mod z squared. That's all I care. Or I should say area. No? So then this is less than some constant times this times mod z squared to this 1 over p prime. But 1 over p prime is this thing, so it's 1 minus 1 over p, like this. Yeah? Cool. So that is just the integral of this thing. So the actual average value, so let's call this from star. So from star, then the absolute value of u of x of mod z is going to be, let me differentiate lines a little bit. Is less than constant times this thing, LP, C take omega, yeah? And then this guy divided by something which is like mod z squared, so then this squared thing will just vanish, so then it'll be times mod z to this minus 2 over p, like this, yeah? Yeah. And p, we have the right to choose it to be anything which is bigger than 2, right? But to get the most decay possible, then we want to make it as close to 2 as we like, right? So take p is equal to 2 plus epsilon, and then we'll have the decay required that this thing is just some fixed constant, right? But as z goes out towards infinity, then the gradient of the partial gradient of u with respect to x is going down to something like a constant mod z over alpha, where alpha is as close to 1 as we like. Yeah? Yeah. So u of x mod z is less than this constant. So I'm just going to write, I feel guilty if I do that. Or I'm going to just write, still going to write the LP norm, but then over mod z to the alpha, where alpha is close to 1. Sorry. Yeah, where for alpha, which is between 0 and 1, but better to choose it close to 1. Yeah? And that was just for the partial of this coordinate u with respect to x, but we can pick up all the other guys in the same way. So we can do exactly the same thing for the partial of v with respect to x. Yeah, it's just line by line identical. Yeah? Because all we used was that this thing is equal to this thing. And if we want to get the partials with respect to y, we can also do that. Let's erase some board. Well, actually, we don't need to do anything else because we have the Cauchy-Riemann equations, right? So once we have this bound for u of x, then since u of x is equal to v of y, then it automatically gives us the same bound for v of y. You know? And the same argument, we have this for v of x as well, but v of x equals minus u of y, so then we have the bound for u of y too. Yeah? So all the partials of either one of u and v are going to have the decay that we want. Yeah? Cool. So we have that it is indeed the case that the function we've created f is such that all its gradients are going down towards 0. If we think about this as a function from R2 to R2, then f is decaying in every possible gradient of each coordinate, and our function g, which was equal to f of z plus z, is looking more and more just like this identity function z. Yeah? So on the outside, we are indeed very close to this flat function. Cool. All right. Let us talk a bit about how with a mathematical, like a cartoon sketch of how we can get invertibility without going too deeply into technical things. From multivariable calculus, if we have a function which is, let's just do everything in R2, of course it works in Rn, we have u contained within R2 going into R2, which is invertible, well, smooth and invertible. Then we know that the area of the image, so I'm going to write area of the image in like this. So denoting mod as like this, as 2D area of set S contained within the plane. Then we know from calculus that the area of the image of any set, let's say P, is equal to the integral around P of the determinant of the gradient of U, like this. That's what you know from calculus, right? Yeah? And this is not hard to see because it's true for an affine mapping, right? It's true for if we just have a linear mapping, because that's one of the properties of the determinant, right? And if we just do an arbitrary domain, all these calculus formulas are proved the same way. We just cut things up into little bits. where it's almost affine. We know it's true where it's almost affine. There's some small errors. We add together all the little bits, pass the limit, have a Riemann sum, pass those limit, and get this formula out. So this is not a surprising or difficult formula. Yeah? Cool. So, but there's a harder but more general formula. The more general formula. And maybe, I know this from geometric measure theory. I don't know if I should say this is a subject, like a theorem in geometric measure theory, but nevertheless, the only references I can give you for this are geometric measure theory books. Let's do a double integral just to remind ourselves we're in 2 dimensions. If, instead of doing this thing, if we do the following, let us do this. Let us integrate over the image of the set like this, and let us count the number of pre-images for each point in the image zeta. Let's count them. So we're not assuming invertibility anymore. And then let's integrate like this. Then this thing is also equal to integral in the reference domain of the determinant like this. The x if the determinant of u is positive almost everywhere. That of the u is bigger than or equal to 0. So as you guys know, the fact that the determinant is just bigger than or equal to 0 doesn't mean it's invertible, right? So there can be some non-trivial pre-images, right? So I sort of recall like z goes to mod z squared. This thing has got determinant positive everywhere except 0, yeah? But it's certainly not invertible, yeah? Because it wraps the complex plane around itself twice. So if we had this kind of domain like this, and then we applied this thing, yeah, then the image would be something that wrapped around itself more than once. And then we can apply this theorem to that particular image here. Yeah. So so the image would be like this thing that looks kind of like an annulus, but there's this overlap in it. Like I can't really draw it. Like there's this overlap region like this. And then if we integrate over the image, then over the overlap image, if we integrate over the image, then this thing is counting the number of pre-images. Yeah, and a lot of them, there'll just be 1 pre-images, but some will be 2. But that thing is still equal to the integral of the determinant over P in the reference configuration. Right? So if it's an invertible mapping, we get back exactly the same formula. If it's not invertible, we get a more general thing. Okay? So this is the area formula. And we're going to consider as a toy model. So as a toy model, am I over time soon? If we take, suppose we have u from, say, R2 to R2, smooth, the determinant is bigger than 0. Let me not say that. Yeah, just say it's smooth. And we have some ball on which this guy is equal to the identity on the bound of the ball. U of x is equal to x on the boundary of the ball. And we're thinking of the ball as being increasingly big. Right? So we have a very large ball where the mapping can maybe do weird stuff inside the ball, but on the ball itself, on the boundary of the ball itself, it's equal to the identity. Yeah? And let's have determinant of the u is bigger than 0 on the ball, like this. Then the integral around the ball of the determinant of the u, like this, will be something we can actually calculate. It'll be something we know. Any idea what this thing is? So these are only conditions, but I claim we know exactly what this is. So this is the determinant. So if you write it as divergence, then it'll be like this: u1, u2, comma 2, minus u1, u2, comma 1, like this. Yeah? So if it's a divergence, then we can just then by divergence theorem, it's equal to the integral around the boundary. Let's put double integrals to re-emphasize them in 2 dimensions. Now this is equal to the integral around the boundary of the ball, right, of this vector field like this. Dot product, the outward pointing normal, dh1. Yeah? So it only depends on its boundary values. Yeah? But its boundary values, it's just equal to the identity. Yeah? So that means that if instead of having this guy, if we replaced this guy with something which was just the identity, yeah, then again it would satisfy exactly the same conditions. Yeah? But if we had just the identity, then the determinant is equal to 1, and then this thing is just the area of the ball. Yeah? So the moral is that if we have the determinant and we don't put absolute value signs around it, then the integral of the determinant is just depending on the boundary. Yeah? And therefore, this thing would be exact. So we can't tell actually what's happening in there. Like, it's irrelevant what's happening to this guy in the interior. It's all being cancelled out when we do the integral. Yeah? So then this thing is exactly the same as what happens if you happen to be the identity. If you happen to be the identity, then the determinant is just 1. It's just the area of the ball. Yeah? So only depends on values on the boundary of the ball. So this, you could be identity, and we can't tell. The integral can't tell. Let's call this thing star. Huh? Can't tell. Yeah? So star, therefore, is just equal to pi r squared, just like this. Yeah? These hypotheses are sufficiently strong that it means that this thing is explicitly just pi r squared, no matter what function u does, so long as it has these boundaries, this boundary value. Yeah? Cool. So if the image of the ball of radius r is simply connected, then it has no holes, but the image of the boundary of the ball is just the boundary of the ball because it's the identity. Yeah? Yeah? So, well, I should say the boundary of the ball of radius r is contained within the image of the closure of this ball, like this. Yeah? So if this guy contained no holes, then since the entire boundary of the ball is contained inside it, then the entire ball is contained inside it. Yeah? So the ball of radius r is contained within this guy, like this. Yeah? So we must have that the area of this guy has got to be bigger than or equal to pi capital R squared, if it's simply connected. Yeah? But then, what does our area formula say? So we are integrating over something that has area at least pi r squared. We're doing this pullback, so this is always at least bigger than or equal to 1, right? But on the right-hand side, we have that the integral will just be equal to pi r squared itself. Yeah, so I'm running out of board and time, so I'm gonna, okay, I'll write it. So by the area formula, we're gonna have that integral of u of p of r, let's count the pullback. Obviously, sometimes this is infinity, but part of this theorem is that for almost every point in the image, it's not infinity. Oh, I should integrate with the zeta, since zeta is a variable in the image. Zeta is equal to this right-hand side, but this right-hand side we've understood has to be equal to pi r squared. Yeah? Okay, so since this is bigger than or equal to pi r squared, yeah, the only way this is possible is if it's actually just equal to pi r squared, and this thing is equal to 1 almost everywhere. Yeah, and since we're smooth, it's actually equal to 1 everywhere. Yeah? But since in the image we definitely have at least one pullback, so this implies that is just got area of pi r squared, and since smooth, oops, cardinality of the inverse is just 1 everywhere. Say it louder. So in this cartoon sketch, we have the function which is smooth. It's equal to just the identity on the boundary of some ball. Yeah, the determinant is positive everywhere. Yeah, and then if the image is simply connected, and that's a non-trivial thing, but if it is, then this area formula concludes that we are invertible. Yeah? And this situation is not a million miles away from where we are, because what we have is a mapping which has got derivative which is positive everywhere, it's like almost everywhere. Around the boundary, it is looking more and more just like the identity. Yeah? And if you accept the fact that we have to deal with some non-smooth part where we actually have mu and it's not where we actually have omega, it's not holomorphic, and then there's like some difficulties there. Apart from that, and apart from the fact we don't quite have an identity, but we have on the boundary, but we have something which is closer and closer, you can start to believe that this has to be true. This has to be true. Yeah? The actual argument, requires more sophisticated things, but just to give you a flavor beyond the plastic bag metaphor or the rubber sheet metaphor, that's why these hypotheses, these things we've concluded about our function f, and therefore about our function g, should let you believe that it's actually invertible. Yeah. well, the problem, so this formula is true for Lipschitz functions, and I think it's true for Sobolev functions. So we still have this general formula. The problematic part with trying to do a sketch of this kind is that we don't have an exact equality anymore, because we don't have, so I'm using an exact equality here to say that every preimage is, and that's not the case. So if I try to do an argument like this, what I would be able to conclude was that more and more of these points are invertible. Like there's more and more preimages have just one element. But would that be enough to actually conclude it's invertible? I don't know. Maybe because the error gets smaller and smaller as we take bigger and bigger balls, maybe there's a kind of argument that if there is a set of positive measure where the preimages are more than one, then by taking a large enough ball, we'll get a contradiction. That's possible. And we also, this is something I skipped over, but it's non-trivial to conclude that this thing is simply connected. But I think it is true. There's a homotopy type argument, so simply connectedness is a topological invariant. We could take a homotopy from U just to the identity map, and I think that would conclude that it's simply connected. But yeah, that's a nice exercise. If you want to try and make this a rigorous argument for our situation, then give it a go. Maybe it's possible, but yeah, I'm happy to just give you a sketch and then ask you to believe. Cool. All right. So pleasure. So after spring break, we are going to start talking about the background necessary to get to this point, which was proving that the Beurling transform was bounded in LP and controlling its LP norm, showing that the LP norm tends closer and closer to 1 as P tends towards 2. That was the thing that we used in this argument. That was like the key thing we used, right? We have that the Beurling transform, the LP norm, yeah, it is a famous conjecture, and it's been around many years. If you want to be instantly famous, then solve that problem. So I'll state the conjecture when we get to it. Actually, one of our faculty, Leonid Slavin, is exactly working in the area of calculating optimal norms of various operators that come from harmonic analysis, and it's something called the Bellman function, or the theory of the Bellman function theory. So it's a particular technique of trying to estimate norms with this kind of geometrical approach of interpreting it and in a certain way as a certain kind of thing which is convex on some domains, or convex along certain lines on certain domains. And very smart guys work on that area, and they've been very trying to get this this conjecture for decades. And they've inched and they've inched and they've inched, but they haven't got it. And so it's probably a hard problem. But maybe he knows something about it. Maybe he's like not in sense of worked on it, but been in seminars where it's been discussed. So maybe I'll ask him about that. A very interesting topic and very deep papers focused on that exact thing. All right, I'm well over time. Sorry, guys. Have a good spring break, and I'll see you all week after next. Bye-bye.